Thank you all for coming. This workshop aims to present the final report on Task 41 results. And we have here some speakers. We have Robert Dickinson, who has been task manager for the last years. We have Herib Blanco, who has been a task expert, and he has contributed to the task obtaining to the results obtained by the task. And we have our chair Paul Lucas, who will be doing an introduction to the Hydrogen TCP. So we will be presenting some slides with the results achieved, and we will start with the presentation of the Hydrogen TCP. So Paul,
can you share your two slides?
Yes.
I think it will be better than I will do.
Great. Yes.
So
I will.
Hello, everyone.
Yes,
so
I believe they can hear you.
Sorry?
Yeah, I believe they can hear you. So
yeah, maybe I can just show my face a few seconds, because maybe it's better for the flow. So thank you very much. I am very happy to open this final workshop on Task 41, because I consider Task 41 was a very important task in the TCP portfolio. I will be very short, just to remind you that we are, as a TCP international organization, international platform, to carry out some analysis, some R&D studies, and to accelerate the hydrogen deployment in this special time where we know a very big hydrogen momentum. And you see on the slide that we have more and more members, and new members are joining probably next year, maybe 3 or 4 more. And the last one were Ireland and Morocco. And so I think we have a very good representation. We are a lack of Latin America, but we are working very hard to attract maybe 3 or 4 countries next year. We have very good hope that they will join, and maybe in Africa to have more countries. Our TCP is very old, because we were created in 1977. We are the oldest organization, international organization on hydrogen. And we are working through Task, as you know. And just, Olmar, the next slide is just to give an overview of the Task portfolio. And you can see that we are renewing completely our Task portfolio, because most of the tasks now are quite new or very recent, and we are in the pipe a lot of new tasks in definition. You can see on the left side. So you can see that we are task on energy storage, on underground storage, on safety, of course, on hydrogen from nuclear, on renewable hydrogen production, on offshore wind hydrogen production, and the last one on very new for us, hydrogen certification. And we have in the pipe a very interesting task in natural hydrogen, hydrogen for industry, hydrogen for LCA and societal and environmental aspect, etc. So, and a very interesting one for us, international hydrogen supply chain, because it's more focused on technico-economic aspect. So what I want to say about Task 41 is that it is a continuation of an effort on analysis of how we can model hydrogen in the scenario. It was started, I remember, a little in Task 30. There was a part dedicated to that, and after in Task 38, we have also a part dedicated to the comparison of modeling tools for hydrogen in the different scenario. It was very interesting, and I remember a very interesting workshop in Bath, UK, where we discussed a lot about why hydrogen at this time, it was in 2017, hydrogen was not represented in the hydrogen scenario. And after the conclusion of the Task 38 was to say that we need make a permanent effort on this aspect, analysis and modeling of hydrogen technology. It's the reason why we push a lot the creation of Task 41. And so I will be very interested by hearing the main results of this task. And I encourage you or other people, I will say to think about a successor task about the same topic, because I think we need a permanent effort on this aspect. So if any of you has any idea to continue the work with the Secretariat, we will help you, we will support you for the creation of this task, because we consider this topic is very strategic for our TCP. And as we are entering in the new strategic phase to 2025, 2030, we will put in a high priority this topic also. So thank you very much, all participants, because I think you work hard and the result will be very good. And so I give the floor to Olmar again. Thank you.
Okay, thank you, Paul, for the introduction. Yes, we're very interested in continuing with these works. And as you can see, we have many tasks open and more to be open. So if any one of you is interested in participating in any other task, you can contact us by email, or if you're interested in following what we will be launching and everything, you can follow us in our social media and you will get the latest news. So thank you, Paul, again. We will go with the Task 41 introduction, and Rob Dickinson, as I said, Task Manager, will be doing it. I would like to introduce you to Rob. Rob has decades of software development expertise in systems design and computer science at the University of Waterloo and companies across North America. This experience includes Advanced Visual Systems in Boston, in Oregon, and in Colorado, and other Mountain View, California, and Ontario. And Rob lastly founded Hydrogen Systems in 2028. So he will be started the presentation of the introduction. You're mute, Rob.
Thank you. How many people do that? Anyways, yeah, thank you. You're doing a fantastic job. And thanks to the entire crew from IEA. And for those who haven't, well, I guess no one has seen it yet, the image on the right is a rough rendition of what the final report graphics designed in Madrid will look like. It's possible that will be delivered during this workshop, but we'll see. If not, be very, very, very soon. So moving on. So some of the key highlights from Task 41 have been that the data is very complex, and hopefully Daria will be here just in time from the Hydrogen Council to bounce around possibilities of what so far is just an idea, but I think it's a great idea to hand off the whole data project to the Hydrogen Council, because there's so many industry members of the Hydrogen Council that are very well poised to contribute to the need for modeling data. I'll get into that in a bit more in a moment. And then the subtask B, which I was task leader on, and Herib will be talking more about, was dealing with diversity of hydrogen, diversity of modeling software technologies, not just the tried and true ones that have been around for decades. A recurring theme that came up quite a lot is the challenges of how do you balance the need for resolution to get accuracy against tractability. You can't spend forever in a day doing number crunching on a given analysis. So that's quite a challenge. It's, again, just an idea, but for me, it's not rocket science to try and develop a multi-resolution modeling arrangement where different models share data. One is really high resolution and the other one is longer time steps. They share data back and forth. I'll get into that towards the end. And then subtask C will be, Paul Dodds is here and we'll be talking about ETSAT, for those who aren't aware, is another TCP of the IEA focused on analysis, energy systems analysis. So yeah, they do lots of good work in collaboration with the Hydrogen TCP to try to get hydrogen integrated into ETSAT. A lot of people were involved, well, at least in the sense of Teams and Zoom meetings, very bit towards the end in terms of rolling out the final report, but it's done now, finally. So the final report contents is 4 chapters with the data at the beginning. But the introduction was what I'm giving right now on the right-hand side. I'll go on to talk about data, and then Herib will pick up on towards improving current modeling methods. And then Paul Dodds will talk about integrating hydrogen into ETSAT models. I've got one slide to recap. What's been really interesting is that regardless of whatever the motive was for Task 41, originally what we've actually observed is that over the duration of 2018, 2019 to now, a very steep ramp in interest in modeling to do with hydrogen. And it's not just academic modeling in the journals, it's also things like electrify everything from in the US and Australia and probably elsewhere too. And hydrogen was integrated into Plexos in 2020. That was right in the middle of Task 41. Plexos being a major modeling tool by Energy Exemplar. It's used around the world. So we can't take credit for modeling, the increasing modeling, because it's happening anyway. So in some ways we ended up having a hard time keeping up relative to there wasn't enough work on modeling. So just to recap the context, and Paul, I guess, already mentioned Task 38, which was Power to X, went from fringe to mainstream over the course of Task 38. It was quite similar to Task 41. So the notion of modeling hydrogen went from fringe in 2018 to becoming mainstream by about now. We're just in some ways documenting that change. So a bit more detail, the state of the industry internationally. People didn't really get, if you like, or understand the opportunity for hydrogen in the mid-2010s. And now, a key quote from the task definition for Task 41 was to improve collaboration between TCP and the ETSAT. So people starting to get it, and hopefully by the end of Task 41 publication, people will get it in a much deeper way. And then similarly, in terms of industry, things went from constrained due to deficiencies in modeling to now first hydrogen roadmaps, national roadmaps began to emerge in 2018, and then now they're quite widespread, with even enterprises reaching financial investment decision on very large scale projects, like multi-tens of megawatts in some cases. Be nice to see stuff happening on the ground, but it's a huge start compared to where things were when we first started Task 41. And again, this is another way of characterizing it in terms of the scale of typical electrolyzers. 1 megawatt is still the largest electrolyzer around Australia, which is in here somewhere, but they've been around for a long time. megawatt scale is coming and gigawatt scale is just around the corner. And another characterization of Task 38, Task 41 context is IEA Hydrogen, the International Energy Agency, where the Hydrogen TCP and etc. TCPs underneath the IEA. They started getting seriously interested in hydrogen for the G20 in 2019, and then they started an annual global hydrogen review, which is now a major project that's reviewed by, has peer review input by people all over the world. So, I don't know how I'm doing for time, but yeah, just to recap quickly, subtask A was about data consolidation. Subtask B was about improving current methods. And C is this, what Paul is going to be talking about. I guess we'll do questions at the end. Will we? Oh, yeah. D was a review of reports from IEA, but really that was just a relatively small chunk of work where the IEA was doing reports, their own reports involving hydrogen, and led by Ali Lind, who was the task leader at that time. We provided some input to IEA's reports. So we made good strides, but we didn't get there in the end. And hopefully Daria is here. Is Daria here, Omar?
Not yet. She will be connecting, I hope that in a few minutes. So she's not here, so you have time.
Okay. Given that she's likely to connect, I better that we wait. Is it for like slot her in later or something? I don't know, because I could present her 2 slides, but
okay.
I'll do a couple of slides just quickly, and then if she comes, she comes. So yeah, so I'll go straight from this one to Darius. Yeah, so guys, the main thing here is the constitutive properties. How do you get data from manufacturers about the performance of their hardware? That was a really difficult issue because no one wants to give away some of their proprietary information. But one of the things that Daria did for, and that the Hidrogen Council did for the critical minerals report was to have a clean room where data came in one side of the clean room and went out the other side, and so people using the data had no clue as to whose data they were looking at. That's where Daria would come in, but she's not here yet, right? So
yes, I'm trying to connect with her.
What do I do?
I believe she's here. Okay, so hello, good morning, Daria.
Just in time. Daria, over to you.
Excellent, thank you. Thank you and congratulations on the launch of and the successful launch of this report. I'm Daria Nochevnik, Director for Policy and Partnerships with the Hydrogen Council. Many of you are, of course, familiar with the Hydrogen Council and the work that we do. As you know, the Hydrogen Council is a global coalition of CEOs representing some 150 industrial leaders in hydrogen around the world, from Europe and Africa to the Americas and Asia Pacific. We work a lot on syndicating industry data and providing some data-driven analysis of the development of the hydrogen economy globally. Many of you are familiar with our periodic Hydrogen Insights reports, as well as the work that we do on modeling the development and the outlook for potential cross-border trade flows in hydrogen. We will be soon releasing the next iteration of our global trade flow study, where we model some 1.5 million potential trade routes in hydrogen and derivatives, and how those can evolve on the time in the short to medium term, as well as in the longer term. Now, the topic of hydrogen system modeling and hydrogen system integration is one on which we are working very intensely. And in fact, the Hydrogen Council has been developing our own modeling work based on Plexos. Many of you may be familiar with this tool. I am pleased to share with you and also to let you know that we will be soon publishing a dedicated study on hydrogen integration in the energy system, and which we have been carrying out together with Baringa. And in this presentation, I will share with you a couple of insights and a preview, if you like, of this work. I'm just going to do screen sharing now to share my screen with you. Just give me a minute, please.
In the meantime, I would just like to thank you for your presentation and add to that your task manager of task 47 hydrogen certification, the one that Paul presented in the task for portfolio status. So Daria is also EXCO representative for Hydrogen Council, so she's a very active member of the Hydrogen TCP.
Thank you so much, Omar. Yes, indeed, we are delighted to be managing Task 47 on certification. And of course, there are many, there are multiple items related to the interplay between, of course, the physical market and the market for environmental products, for hydrogen and derivatives. That is all to be considered. And I'm sure that we'll have, there will be great opportunities for synergies between our tasks as well. But going back to the topic of hydrogen integration in the energy system, so we see that indeed, as hydrogen energy is set to penetrate across different segments of the value chain and different segments of the energy ecosystem, it can help indeed unlock enormous possibilities when it comes to reinforcing energy system resilience, cost efficiency, and of course delivering on our net zero objectives. So as many of you know, we see that, of course, hydrogen integration in the energy system goes very much hand in hand with direct electrification. As you know, that hydrogen enables indirect electrification with molecules and ultimately can also enable cost-efficient long-distance transport of these renewable electrons through molecules. We also see the opportunity for hydrogen to maximize those cost efficiency benefits of greater renewable energy penetration in the system. So of course, making sure that that valuable renewable power that is being produced does not go to waste with curtailment, and we avoid, of course, the associated system cost of curtailment that we observe across multiple geographies today. Importantly, the hydrogen integration will play a key role in enabling that greater flexibility and resilience of the energy system, both short-term flexibility by way of providing grid balancing and ancillary services to the power grids, and of course long-term flexibility thanks to greater synergies with the repurposed gas networks and storage to cater for seasonal demand. So that's response to seasonality will be critical going forward, as we know that catering for seasonal demand is something that historically has been provided for by heavily polluting fossil fuel sources. And last but not least, if we take a step back, of course, looking beyond power and gas networks and looking at the downstream segment, we also see that deployment of hydrogen and fuel cell solutions can help foster some healthy competition. For example, we have modeled the sun-to-wheel efficiencies of FCEVs and battery electric vehicles, and we see that at whole system level, if you also consider the impacts of, again, the renewable power system balancing and alleviating the curtailment inefficiencies, those whole system benefits of FCEVs and EVs are actually comparable. And in that sense, deployment of both solutions and not picking winners can in fact help foster healthy competition among the solutions that allow us to pave the way for decarbonization of the relevant downstream sectors. And of course, transport is a heavily debated one, but a good example of those where maybe some of the historical biases may need to be alleviated, and there is definitely a case for opening up to healthy competition between multiple technologies. So within the Hydrogen Council, like I've mentioned, we have undertaken the work on modeling hydrogen integration in the energy system together with our colleagues and partners in Beringa. We have used Plaxos as the modeling tool, and we have looked at 3 distinct regions with very different energy systems: Central Western Europe, Japan, and Texas in the US. And what we have aimed at doing is really to assess and quantify the impacts of hydrogen energy penetration across power, gas, and liquid fuels, using the latest iteration of Plaxos that allows you to explore synergies between those 3 elements of the value chain in sort of an integrated manner. And in particular, the insights that I have shared earlier, of course, are very much confirmed by this modeling and the analysis that we have carried out across the 3 regions. We see that both energy efficiency, sort of cost efficiency, and climate benefits associated with that greater integration and unconstrained performance of and availability and the opportunities that are associated with effectively letting hydrogen solutions such as electrolyzers be integrated in the system in an unconstrained manner where they're able to follow market signals, that can unlock substantial benefits. And we are very keen to share with all of you some facts and figures and some quantified insights, quantifiable insights based on the analysis that we have carried out. In the coming month, we will be releasing the report, and we will be, of course, sharing this hopefully with the task and with the wider group and we'll be keen to have a deep dive into some of the results of this exercise. So I'm going to leave it here, but of course the topic again of modeling that hydrogen integration in the energy system is one on which the Council is working very actively these days. And again, we congratulate Task 41 on the deep dive report on the modeling considerations for hydrogen. And we're very keen to share the results of our upcoming study with you in due course, as it will be going live within the next couple of weeks and months. So with that, a big thank you. Congratulations to Robert and the task. And it's a pleasure, of course, to continue our exchanges on this critical topic. Thank you.
Thank you very much, Daria, for your presentations. Does any one of you have any question? If you have a question, you just need to raise your hands, and we will let you unmute yourself and put your screen so we can see you. Or you can either comment in the chat.
Or we can save them up for the end if you want. Whatever.
Okay, yeah, sure.
If there's nothing right now. So let's move on.
Thank you, everyone.
Thanks, Daria, for rocking up just in time. That's pretty amazing.
Thank
Okay,
you.
let's wait just 1 minute.
Are you waiting for Herib?
Okay, so no questions. If anyone wants to react in some way, we will. Okay, we have a question.
It's a comment, I think. Oh, that's not.
So Fabian asked, what are the risks and trade-offs of coupling hydrogen? I don't know. if Darius is still here, or if you, Rob, can answer that question.
I'd invite Daria to expand on it, and I guess that, like, I'm not sure if there are all that many risks, trade-offs there. I guess if you go too far down one track, then it might be hard to come back. But it's so early in the day. Just anything that starts to integrate hydrogen and electricity is heading in the right direction. I'll be talking quite a bit more about hydrogen electricity, at least if that's what he's concerned about.
Okay.
It's available on the website. Now we have the answer to the question with the website. The report was I went in 2 stages. I presented the final report in my InDesign version in Casablanca at the end of June, and it's been undergone a very slick, professional graphics redesign process, and will be available anytime soon. Maybe even by the end of this webinar, but we'll see. Yeah.
Yes, that's it. It would be available today, but as you are registered for the workshop, we will be sending to you by email, so you can have it, because we believe that you have special interest. So as soon as it is published, we will forward to you. Okay, so I think we can continue with the next section, right?
Yep.
Okay. I believe that now Herib Blanco will be presenting. I would like to introduce Herib to you. Herib has 14 years of experience, out of which the last 7 are on hydrogen. He has worked on hydrogen at the International Renewable Energy Agency, the IEA, the Joint Research Center of the European Commission. His focus has been on technology development, cost analysis, and policy development across the entire value chain, and also including some of geopolitical aspects of hydrogen trade. His contribution to the Task 41 was as a sub-task leader and author of the publication that will be presented today. So thank you, Herib, for being here today with us, and the floor is yours.
Thanks, Omar. Yeah, good day, everyone. So today, as was said, I will present you about an article that we wrote it took about a year and a half. The article is about taxonomy of hydrogen energy system models. Perhaps 30 seconds of background is that the reason for this is that I think in the last 4 years or so, hydrogen has moved. Historically, it had the focus on vehicles, mostly because of the oil crisis. And only in the last 4 years, I would say it has expanded the scope in terms of on the supply side, flexibility for the power system, but also looking at derivatives, trades, and other aspects. I think that's a relatively recent trend. And the link is that has opened up the complexity, that has increased the complexity of modeling hydrogen. Therefore, there are many types of models to use for hydrogen. And then that's what leads to requiring a taxonomy to characterize those different models. So that's the context of today. What I have in mind is to start with a 2-minute version of the work for you to have an idea of what are we talking about here, followed by a longer version of basically the more details. So the 2-minute version is that what we did was, the approach was to first define a model taxonomy. There are many articles that go into defining a taxonomy for an energy model. So we did a review of almost 30 articles in total that define a taxonomy for energy models in general. So that was a starting point. In parallel, we also did define these archetypes, the different types of models that are used for hydrogen, because I think there are kind of different communities, if you might say so, where each community has a specific approach. To be more specific, for example, there are many articles around hydrogen supply chain and optimizing the infrastructure, where are the stations, where are the pipelines, and kind of the geospatial analysis. But the point here, there are kind of these pockets of information that do not interact that much with each other. But so the second step was to define these different types of models. Third one was to combine these two. So use the taxonomy to characterize those archetypes. So again, when I say archetypes, are the different types of models for hydrogen. And last was to identify commonalities, gaps, and challenges once we use this taxonomy. So in terms of key messages, starting with the end in mind, so what we find rather than going through the whole analysis. One is that hydrogen, you use it across the entire energy system. It's like electricity. So then you need, it's a complex one that you need different models to cover holistically hydrogen. So no single model can cover everything. And again, I would say this is the most important. Soft linking of different models is required. And soft linking just means coupling, putting one data, the output from one model to as input to another one. So soft linking of models is required to have that holistic answer for hydrogen. That's one. Second is that, as I said, hydrogen is a versatile energy carrier, and it has specific features that it requires for modeling. I will go through it in the longer version, but for example, one is that it has a system-wide scope, and what I mean is that you can use hydrogen anywhere, again, similar like electricity. So if you use a power model, perhaps making the link with what Daria just presented, if you use a power model, then you ignore uses in industry, for example, ammonia for shipping, that is transport, the same synthetic fuels for aviation, and so on. So the point is you require a system-wide scope. That's one. Also the flexibility to the power sector, and the possibility to compete with other options like demand response, storage, transmission expansion. That requires high temporal resolution or of at least hourly resolution. So I have in total 8. I will go through it through those in the long. Requires a specific modeling. The third one is that some of the categories, as an example, and when I say categories, means items that we use to characterize, to have in this taxonomy to characterize a model. One is that some of them, like renewable hydrogen production, so the electrolysis pathway, that's pretty much everywhere. But another dimension, as an example, the environmental impact is only covered by a few archetypes. So yeah, some of them are covered, some of them are barely covered. The fourth one is that we also identify correlations between the different archetypes, and then some of them are overlapping to a large extent. So for example, an energy model with an integrated assessment model, and even a power model, they're similar when you think about there are other types of model like environmental life cycle assessment, which is very different. So it depends on the point of reference, but again, I'll show you some more details there to back that up. In terms of gaps, the main gaps are environmental impact. So the life cycle assessment, that's relatively new for hydrogen. And when I mean environmental impact is the combination with energy models. That's the new part. There are many studies that do LCAs of hydrogen technologies in general, but the integration with energy system models, that's what's missing a bit. The innovation cycle, what I mean there is the endogenous learning rates, the S-curves, the tipping points for different technologies, and how technologies go through the innovation cycle from early R&D to demonstration to commercialization. That's something that's not well represented in most models, and it's usually just part of the data input. Market design, both for the power market and the flexibility that electrolyzers can provide, but also for the end use side and the hydrogen market that is relatively new. That's, again, not well covered in most models. And policy is usually done with constraints, but not much more in detail regarding implementation impacts, societal and equity issues. So that's also something that could be further explored. And the last one, and probably have taken more than the 2 minutes that I said, hydrogen technologies are relatively new in some archetypes. For example, integrated assessment models, which are the ones used for IPCC. So consistent validated set of data is for all those models is lacking. So the longer version, again, just similar to what I explained you, but giving you more details. So this is a taxonomy for any energy model. So again, for this one, we reviewed almost 30 articles, a total of 127 categories, which we cluster into these 6 majors that you see. And I'll guide you quickly through each. So yeah, one way to look at a model is what's the purpose. You could look at a normative scenario. What do you need to do to reach net zero in 2050? You could look at it in a forecasting way or exploratory, starting from today. What happens if I increase the carbon price to X as an example? So exploratory. But the main point is that, yeah, depending on the purpose of the model, that already, of course, gives you a difference between one another. The other is solution methods. Around the analytical approach, for example, if it's top-down means if you start from the macroeconomy and then try to model the technologies, or bottom-up, where you have very rich technology detail, but not so much of the macroeconomy. That's an analytical approach. Mathematical approach is just if you have optimization, simulation, system dynamics. There are different types, and they will lead to different answers and different insights. So that's another way of, let's say, slicing and differentiating the models. Use and accessibility is just because of the recent trend, well, not so recent anymore, of open modeling. So just if it has transparency and the licensing and training. Another one to characterize models is the structure. So what parts of the value chain are covered, if all the derivatives, hydrogen derivatives are covered, all the end uses for those derivatives. Again, if we look at probably shipping, ammonia for shipping, methanol for shipping, and aviation, those are relatively new, and many of those are not covered in the models, just because there's a lack in the updates, right? The other is spatial-temporal issues. So what's the time horizon and the resolution? If you look at models that cover decades, integrated assessment models, for example, it's hard to find the hourly resolution just because there's a compromise in the computation and the tractability of the model, and the same for the spatial scope and spatial resolution. And it links to the purpose of the model. If you're looking at trade, probably you need to do more than 3-4 regions in the world, of course. So it links to the purpose. And complexity, these are, because many of the models are based on cost optimization, but not everything is driven by cost. There are some, what I call irrationality. For example, in buildings, users not always go for the cheapest option, and the same for cars. There are other factors, safety and brand and others, that go into the choice. So taking a step back, the whole point of this slide was to show you this is the general taxonomy for any energy model. Then if we look at the modeling features that are required for hydrogen specifically, I think I already explained the first one, system-wide scope. The second one as well, the flexibility to the power system, the possibility of ramping up and down the electrolyzers and competing with other flexibility options. Spatial temporal resolution, that's at least hourly is needed to capture the benefit of the flexibility of the electrolyzer. Hydrogen doesn't have greenhouse gas emissions at the point of use. So then it's the importance of using life cycle assessment and capturing the upstream impact, methane emissions, electricity footprint, CO2 footprint, and so on, but also to look beyond greenhouse gas and look at other impact categories. Systemic drivers, what I mean is that hydrogen is one of the technologies that touches upon the entire energy system. So then its role depends on the assumptions for other cross-cutting technologies, such as CCS, nuclear, and bioenergy. So the less you do of the other ones that I mentioned, then the more you need of hydrogen, and vice versa. So it's affected by that. The consumer behavior, because of the aspects I mentioned in buildings and cars, for example, and road transport. Development uncertainty, just because hydrogen is a relatively new, novel set of technologies, and then if there are many projections on the costs going forward, but all of that has a very large uncertainty. Yeah, so then it's the role of hydrogen depends on that. We don't have much reference for that. And climate variability, I mean, yeah, at the end, one of the core technologies for hydrogen is the renewable pathway. Wind is there, and then wind depends on the climatic year that you take. It can vary a lot from one year to the next. So that's kind of another feature. This leads me to the kind of adapting the technology that, the taxonomy that we saw before. To hydrogen would leave this. So one is a spatial temporal resolution that's key for hydrogen, just because of the flexibility that's in the temporal aspect, but also if you look at the spatial aspect. Yeah, on one hand, you need high spatial resolution for the renewables potential to know where are those renewables located. The same for the infrastructure. You need a high spatial resolution, so that's the reason to have that as a key category in the taxonomy. Model topology, because of what I mentioned for the hydrogen derivatives and end uses, that's key because you only unlock the full potential of hydrogen when you consider the hydrogen derivatives. Those derivatives are the ones that are being traded, and trade is a relatively big part of the hydrogen potential. So that's important, the importance of the model topology. Complexity, I think I already mentioned all those aspects. So it's important to have those to look beyond cost optimization. And perhaps another angle that I haven't mentioned is that part of the complexity, again, that goes beyond cost optimization in trades is geopolitics. You will not look at country X just because of the cost, and that's the export potential or even the land area. When you look at country X, it depends on the industrialization, the political stability, the renewable development, and so on. So my point is that's something that goes in this complexity category and a way to characterize models and the methodology. So looking at the archetypes for hydrogen, we identified 9. We had more archetypes, but we narrowed it down to these 9 core archetypes. So let me guide you briefly through them. So starting, and the way to see this is, I would say, kind of Venn diagrams is what we try to show here. The smallest one is if you look only at one electrolyzer, one renewable plant, and try to optimize the size of those. That's what we call here BRE integration. So just very small scope. Then you could expand that to the entire power system, include some other generators beyond wind and solar, the demand beyond electrolysis, and then you have a power model. But that has a limitation of relatively simple representation of other sectors, even when you see Plexus and the new Plexus with gas, and it has very limited scope for transport, for example, for aviation, for shipping. So it's still limited. Then you could expand it to an energy system model, including the other sectors, but then you start making trade-offs related to the question that was posed in the chat. The trade-off there is you expand the scope and then you cover more end uses, but you probably have to compromise a bit the temporal resolution because then you have a wider set of technologies. There are energy system models that have hourly resolution and cover all the sectors, but then you might compromise on if you're doing operational optimization or capacity expansion, for example, or the geographical scope or geographical resolution. You could expand further scope and do integrated assessment models, so include things like the carbon balance, the climate, land use. So that's a wider scope, but then again, those have even finer resolution, and you might have issues of modeling seasonal storage, for example, which is one of the business models for hydrogen. So that's, let's say, at the core. If you look at the application to cities, it's basically an energy system model, but for cities. So you're changing the geographical scope. Similarly, if you look at islands, there are many articles that look at the role of hydrogen in islands, but those usually focus more on the power sector, just because islands do not have transmission, and then you need the 24/7 supply, and hydrogen coupled with fuel cells can provide that. And that's usually why they focus mostly on power. There are other sort of studies with environmental assessment, so the life cycle assessment bit, which are different. And again, I already discussed that. And the geospatial analysis, which usually the trade-off there is that they link with the rest of the system. They take fixed assumptions for the hydrogen price, fixed assumptions for the demand usually, and then the added value is in where are the facilities located. Many of these analyses focus on road transport, so where are the refueling stations located? How do you reach those stations? Where's the infrastructure, the pipelines, and so on? Yeah, so I'll take probably like 5 more minutes, and I think I'm still on time, but let me know if that's not the case. Yeah, here it's kind of an overview of part of those trade-offs that I mentioned and advantages and challenges of each one. So interior assessment models, those are the ones used for IPCC. There historically there has been a lack in the role of hydrogen there, just because of the update cycle. And even in the recent AR6, the role of hydrogen is still smaller than from other international organizations. So there, the advantage is, yeah, it covers everything, but because of this update cycle, it doesn't consider many of these end uses, and not all of them. And again, particularly for the derivatives and trades, to unlock the full hydrogen potential. For energy, I already mentioned the trade-off of temporal spatial resolution because it's expanding in the scope. For power, the advantage is that it captures the flexibility, but the disadvantage is that it's focused on power, so you're missing the rest, and hydrogen needs the rest. It's a cross-cutting energy carrier. Perhaps not to go through each of these. Another important one is perhaps the last one, the environmental analysis, just because, again, that's a community where there are lots of studies looking at the LCA impact, but not many with the integration. And there, something key is the inventory for the environmental impact assessment. And having the consistency with the energy model. So for example, part of the inventory is electricity use and what's the footprint for the electricity use, even, for example, for the concrete that you use in the electrolyzer, that's called background. And perhaps another last comment is on the right-hand side, the specificity for hydrogen. What I mean there is how much focus is on hydrogen for these different types of model. And as an example, integrated assessment models, those are very wide models where hydrogen is just one of many things. And again, remember, this type of models covering the climate and carbon cycle and land use. So I would say that's the least specific for hydrogen. Whereas in the other extreme, if you look at the supply chain one, so the one with the geospatial analysis, that's purely for hydrogen, like where to put the hydrogen pipeline, where to put the trucks for distribution and the stations and so on. So yeah, this gives you a sense of how specific it is for hydrogen. Something to show here is that what I want to show is that on the left, you have the different archetypes. This is not one-to-one match what you saw before, but yeah, it gives you the idea. And on the top, you have the different modeling features that hydrogen requires. And the point here is that each model has only a couple, covers only a couple of these features. One of the most complete is the energy system model, and then that's why this is usually the one used for hydrogen. But you see some of the features, flexibility for power, like without resolution, and the power sector and the market design and so on. That's something that only the power model can do because it's just specific for that. If you look at the spatial resolution and knowing where each station is going to be and so on, yeah, that's something that only, well, the hydrogen supply chain does fully because that's a focus or spatial analysis. But the point here is that there are some features that are covered by one of the models. And then that's why it reinforces the first point that I had in the key messages, that you need to couple different models to have the holistic answer. But again, it depends on what answer are you looking for. Yeah, that's, and this is the last one. So one more minute. This briefly gives the different types of archetypes here in in the diagonal, and what you see is the correlation between the different archetypes. So for example, geospatial analysis, you see it's mostly red. That means it's not that correlated with others. And similarly for LCA, it's relatively yellow and red. Again, it's another one that is not that correlated with others. But in general, again, it just gives the, so one key message is that those three, so geospatial, LCA, and energy model, is probably one combination that has already a good coverage of all the aspects. That's one. Second is that if you look at integral assessment models, ESM, LCA plus, those are mostly green, which means there's a high correlation between them. So they're relatively similar. If you're doing one or the other, yes, they're different. But again, when you look at it from a broader perspective, they're relatively similar. So I'll leave it here. And then the last one was just to mention that, yeah, this was a team effort. So yeah, thanks to all the team. I think I saw a couple in the call. So yeah, I was the lead author, but by no means the only one. So yeah, just to thank the entire team for the contribution. Thank you.
Thank you, Herib, for your contribution. We will continue with Rob. He will be presenting integrating multiple resolution assessments, and then we will do the question and answer section for these parts. Okay, so just stay for the questions and answer, and we will do it later. Thank you. You can present, Rob.
Yeah, thanks, Herib. I'm going to go fairly quickly through these because we're a little bit late on time with the, after many presentations. But all of this is in the final report, so if you want to look it up and send me an email if you have any questions, that'd be cool. So I use the word hydricity to refer to integrated green hydrogen and electricity. And why hydrogen? It's not just another energy carrier, it's all sorts of other things. So it's an electricity consumer, network balancer, curtailment avoider, as our Indian colleague pointed out just now in the chat. Large scale carrier, fuel source, in the sense of providing fuel to fuel consuming services, and so on. But as one of the things that Herib pointed out is the need for a soft coupling of different systems. That's one way of putting it, but I'll be referring to that at the very end of this short presentation. So ideally, it gets interesting to look at dispatch interval time resolution while maintaining computational tractability. So I reckon we can have our cake and eat it too. What happened? So picking on South Australia as a region with a capital R within Australia's national electricity market. It's where I live, but it's not why I'm presenting it here. I'm presenting it here because it's the world's best example yet of a market that is already suffering from, if you like it to put it that way, or benefiting from it, if you like to put it the other way, of very high proportions of variable renewable energy, so wind and solar. So this is what's happened in the last decade. It's getting close to providing enough wind and solar for, well, actually to backtrack a little bit, the state government wants to get up to about 500% variable renewable energy by 2050 and sort of 200% in the 2030s. So how do we make sense of going over 100%? I'll get onto that. So, oops, sorry. So the demand minus wind and solar, so that just the bottom graph in this presents the interaction of both demand and the wind and solar production. So as you can see, we're getting more and more negative values. That is very low demand in sync with very high varying production. Oops, sorry, I keep hitting the wrong button. So the question is, can you a question I posed, is can you model price as a function of all these different complex things? And the answer is yes. So in each one of these over a 3-year period, obviously it changes over the long term, but over any 3-year period, there's a good shape match between registered retail price, RRP, and all of these other 4 independent variables: demand, production, that's wind and solar production, curtailment, and eventually demand market. That's where we get particularly interesting. So if you look at the history of demand modeling, price modeling, until 2010, there was no significant wind and solar production, so RRP was a clear modelable, is that a word? Function of demand, and then became increasingly dependent on varying production in the early 2010s, and then production plus curtailment in the late 2010s. And so the extension of that is, can we add a demand market to operational demand? So demand market means any energy consuming service that is able to respond to price, to sort of buy or bid into the low price markets. The obvious one is electrolysis. So yeah, this just works. Obviously, things fall over if you've got nothing but negative prices. But if you fill all these negative, so from top to bottom, this is scaling. You could think of this as 2028, 2032, and all the way down to 2050. And everything else is the same. So you've got increasing opportunity to buy or to bid, if you like. This is the price at which these energy consuming services are buying electricity. Yeah, I'll skip over that. So this is the crux of it. Price dynamics modeling clearly shows that anything below 0 is obviously not sustainable. Just the energy system, the market falls over. But so there's no free lunch. You need to have a bidding process to push all these prices up, and then everybody wins if you have a bidding process. So this is why I'm alluding to over a 10-year period from we're roughly here right now. 2030s in here, or 2032s in here. So roughly a 10-year transition period where the history of electricity markets around the world, most of the people that I saw in the attendee list are from Europe. Obviously some from India as well, which is cool. But everywhere around the world, probably India as well, the bids are stacked in order of the lowest dispatch first and the highest last. So if you're a coal plant, you always bid at the lowest price because you know you get in to whatever the price ends up being. But if you're a high price, then if you don't want to go in too low, then you can choose that. And it's the other way around. If your bids are stacked in order of highest dispatch to lowest last, if at all, then that's the demand side is being taken care of by balancing out all of these things. So for me, it's like fundamentally obvious that that's the way we're going to go. You can think of it as fuel to power and power to fuel. So obviously that's thinking of things the other way around. It's fundamentally obvious that as we go from fuel to power, where the fundamental cost of electricity is fuel, and here the fundamental cost of fuel is power. And we need to flip things around. So I just suggested that it screams out for me to have a 10-year modeling project where we start out modeling. You don't actually implement it yet, but start out modeling two sides, a power production stack and a power consumption stack running side by side, and that's not rocket science. So yeah, once you have that, all of that was based on 5-minute time steps. So this top row here is 5-minute time steps, 5, 10, 15. And these are decades or whatever it happens to be. Like it's that model that Paul's, oops, sorry. That Paul's going to be talking about in a moment, or well, anything that has a decade or a 1 year or whatever. It's not, for me, it shouldn't be too hard to arrange to have the benefits of 2 or 3 modeling systems at once. So I got a bit of a break here, but maybe, Norma, do you want to do a break or do I go straight into Paul?
Yes, we will go with the questions and answer of this section. So if any one of you has any question, please raise your hand or write it on the chat and we will answer it. Okay, let's wait because it's a lot of information, so people might be processing. Okay, yeah, we have the first question.
Is that for me?
Yeah.
Press the, yeah, so far, just looking at modeling, it's just the work that I was presenting just now is based on the current, my prediction or expectation that the current system will fall over, let alone be not economically viable. So yeah, once we have all that stuff, we can look at the production side and the demand side, and then that's where all the economics comes out. That qualitatively, I've done some qualitative work in the past that says that pretty much everybody wins. Surely electrolyzers pay a little bit more for power, but the other overall, everyone wins. So certainly the wind, for example, when people win because they don't have to curtail anymore, and yeah, consumers win because the overall system is more efficient. So yeah, hopefully that helps. Ask me again on hold in another couple of years when I get to that point of doing more economic analysis.
Okay, so thank you, Reinhold, for your question. Do we have any more questions? Not for Herib, not for Rob. No, it doesn't look like. So we will do a 5-minute break so you can go to have a coffee, to process all the information and to come back for the second part. And yeah, Rob just shared his email in the chat. So if any one of you has any question later, you can contact him by email. Okay, so we will see each other in 5 minutes. Okay.
Great.
So thank you.
Thanks, Alma.
So, hello, welcome back, everyone. I believe it's time for restart with the workshop. I see our next presenter, Paul Dodds. So I will present him. Paul Dodds is Professor of Energy Systems at the University College of London Energy Institute and the Institute for Sustainable Resource. He specializes in energy system modeling and has a particular interest in modeling hydrogen and bioenergy system and the importance of energy storage. He has coordinated the development of a new UK energy system model, the UK TAMS model, that has replaced the UK Markle model, and he was ex-co-alternate for the United Kingdom. So good to see you again, Paul. And you will be presenting the collaboration with the ETSAP TCP, right?
Thank you very much, Alma.
You can share your screen, right?
Indeed. Great to see you all too. Hello, everybody. And thank you for the introduction there. So I'm going to talk about integrating hydrogen into ETSAP models, but it's for energy system models more generally. This presentation has a number of contributions from my colleague Daniel Scammon at UCL, from Carrie Espegren at IFE, and from 10 Times modeling teams, whose names I'm going to have a little bit later. I want to start by talking a little bit about the uses of energy system models. So why do we care about how we integrate, or why should we care about how we integrate hydrogen into these models? So the key question that these models can answer is, how can I decarbonize my energy system as cheaply as possible? And that's important, particularly for governments worldwide, because most governments work on a cost-benefit basis. And so they look at the cost of an action and the benefit they're going to gain from it. And these models essentially tell us how we can decarbonize while minimizing the cost. And so they give an answer to that cost-benefit question. They also produce coherent decarbonization pathways. And that's important. So that if a government is following a particular pathway, it has confidence that that pathway will lead to, will meet the long-term targets that it's aiming to create. And it has an idea of what the cost of those targets will be. So as an example, this is a few years old now, the UK Clean Growth Strategy. This was a strategy from the UK government that identified scenarios with 3 areas of technology and resource uncertainty that are likely to have a big impact in 2050. So it had one scenario where electrification dominated, a second scenario where there was a much larger role for hydrogen in place of electrification. There's still quite a bit of electrification, of course, but it was very much more of a mixed scenario. And then a third scenario where there was much higher negative emissions from biomass with CCS, which allowed the energy system more flexibility to use more fossil fuels elsewhere. And each of these scenarios was developed and examined using the UK Times energy system model. And you can see the link here. Now, these models are useful because they represent many supply chains. So we start off from resources on the left, we end up with energy service demands on the right-hand side. And we have a number of different technologies in the middle that process primary commodities into secondary commodities, so gas into electricity, for example. And then we deliver those, whether it's through wires or pipes or by road. We have a series of different demand technologies in different sectors, and these models cover the whole economy, which is really important. So try to cover all emissions across the whole economy for energy. So your demand technologies might be lights, boilers, cars, and such like, that meet actual demands for things that we want in real life. Now, this is a very simplistic diagram. In practice, in the residential, this is also a simplified diagram for the residential sector. You'll see that we have a lot more technologies represented here, and we have infrastructure as well as energy production and energy consumption and demands. And then once we get into the whole model, it becomes really complicated. And in a typical model, might easily have 1,000 different technologies represented, say a few hundred commodities of different types, in order to meet, say, 50 demands across the economy, while counting all greenhouse gas emissions and minimizing them over time. So I want to just mention why we did this project in the first place. There was a question we had, which is why was there so much variation in the use of hydrogen between our energy system models? We had concern within the ETSAP community. So ETSAP is the Energy Technologies Modeling Community, which is another IEA technology collaboration program. So we had concern within the ETSAP modeling community that there was quite wide variations in both hydrogen supply and demand between the various models that people were using. And many people have different national models in particular. We didn't know why this was. We didn't know how large the variations were, because nobody had ever really looked. This was just something that was more like hearsay. Now, if there was variations, and we assumed that there was, based on conversations we had, we didn't know if these were caused by local variations. So simply the local energy systems are different, the types of demands are different, the resources are different, and therefore it made sense to have use hydrogen in some places and other approaches in others. So that would be very normal, very proper thing to do. Or was it because that some or all of the models didn't represent hydrogen properly? In which case that was an issue with our modeling rather than an issue with caused by the real world, local variations in the real world. And that would be a big issue that we'd need to deal with in our models. At the same time, there was concern in the hydrogen community, particularly within IEA Hydrogen, that the IEA at the time, and I'm going back to 2017, 2018 here, the IEA saw little role for hydrogen in the future. And there was concern in the hydrogen community that might be caused by the IEA not representing hydrogen properly in their own models, or making assumptions on hydrogen that were not appropriate. There was no evidence that that was the case, but that was the concern. And so ETSAP organized a project which was linked to IEA Hydrogen in order to investigate these questions and try to understand why there was so much variation. And so in our discussion today, I've just introduced energy system models, and I'm going to talk about the comparison of model inputs we did, which was a survey that took place in 2019. I think now that we're in 2023, that's an important thing to say, because many of these models have improved their modeling of hydrogen since. Okay, so I certainly don't want you to take this as this is the current status of all of these models. Some have changed since 2019. Some will have changed a lot, some will have changed a little bit, and some will have changed at all. We'll also, I'm then going to talk about model outputs, which we also did a survey for at the end of 2019 into early 2020. And then I'm going to finish by talking about making some suggestions for best practice modeling of hydrogen going forwards in these models. So the first step was to look at model inputs. So how do we represent hydrogen energy systems in existing models? And what are the strengths and weaknesses? And so we asked each modeling team to fill in a spreadsheet that looked like this, which essentially was a list of what they assume within their model, a diagram of the actual hydrogen part of the model itself, which when I say what they assume, I mean by what are the end uses that are assumed, what types of delivery options, hydrogen delivery and infrastructure options are included. And then for production technologies, delivery and storage technologies, and for end use technologies, we asked them to give us a list of each type of technology and to provide data, input data for those technologies, and how that data varied over time even. So we really got into some detail here. That input data included when it was first available, what the plant size would be if they modeled a particular plant of a particular size, the capital costs, the operating costs, the efficiency, the lifetime. So that there was quite a number of different, there was quite a lot of data that we collected. And of course, not all models used all of these types of data, so it was flexible for the people to put in there. And we did this for 10 models. Okay, so this is the list of the 10 models on the left-hand side. The scope tells you the geographical scopes of the model. So ETSAP-TM is a global model. Times Pan-EU is an EU model, and the rest were national models, the other 8. Primarily in Europe, but there was Japan. And then for all 10 of those models, we had some inputs provided, and for 7 of those models, we also had outputs. So let's talk a little bit about the inputs. So we start off with transport, because historically hydrogen was focused on transport. And so we thought this was the area that most models were likely to have a role for hydrogen if they considered hydrogen at all. And you can see that 90% of models, there was only one model didn't consider hydrogen use in road transport. And that's because NOptimes is a specialized industrial model. It isn't a whole energy system model, and therefore there was no transport sector. But otherwise, every model considered hydrogen in transport, which is what you might expect. When we look at rail, shipping, and aviation, there was much less coverage. In fact, there was only one model each for aviation and shipping, and they're different. I think that will probably start to change soon, if it hasn't already, but that was the case back in 2018, 2019, when we collected the data. Now, for road transport, 2 of the key issues for hydrogen is that a very high pressure of hydrogen is required in order to transport the fuel in fuel tanks. So we often look at 700 bar transport, which means perhaps compressing the hydrogen to about 850, 900 bar at refueling stations. And we also need to have very high purity hydrogen, so it doesn't poison the PEM fuel cells, proton electrolyte membrane fuel cells that are used by most vehicles. And so we're interested to see if the costs of compressing and purifying the hydrogen for the road transport sector in particular were included in these models. And actually they were in most of the models. Now, I haven't included NOptimes here because it didn't have the transport sector, so it was, but 7 of the other 9 models did consider compression costs, and 3 of the 9 did consider purification costs as well. And they can be substantial. Even with hydrogen from electrolysis on site, you can maybe lose 10 to 15% of the energy in order to compress and purify the hydrogen to the level that's currently required. Then we looked at a number of other uses across the energy system outside of transport. Now you'll see there's some big gaps in the middle because we did this in 2 steps. When we first did the analysis, we asked the teams to provide their inputs. We analyzed those, and then we discussed them at a workshop, at the International Energy Workshop in Paris, which I think was in 2019. And as a result of that discussion, we identified 4 areas where people did model uses of hydrogen that we hadn't actually asked them about in their models. And so we added those afterwards, and not every modeling team got back to us with a response about whether they included those in their model. So that's why we have some gaps in the middle, 4 areas. So we looked at it in industry as a feedstock, or for decarbonisation more generally, for example, in boilers, and also for direct reduced iron production. We looked at synthetic jet fuel, other synthetic liquids, dairy industry, building, heat, and electricity. And it varied quite a lot. So quite a few models represent the use of hydrogen for electricity, and some in industry, but the others are quite patchy. We also looked on the supply side. So do they include production plants? All but one, yes. Do they have decentralized hydrogen production? All but one. We looked at different types of delivery routes. So do they actually have any hydrogen infrastructure, or do they just assume that it's produced and then goes straight to the end use? And all but two of them didn't have any delivery infrastructure, but the rest did. And we asked about power to gas. So could you inject hydrogen into the gas supply? Quite a surprisingly high number of models allowed you to do that, 8 out of 10. And could you store hydrogen? 7 out of 10 have hydrogen storage. Where you could inject hydrogen into the gas supply, we asked what percentage of hydrogen you're allowed, and that varied quite a lot, between 2 and 15%. Now, in the case of a couple of models, that's erroneous, because you can't practically put more than 6% in, which is the same as about 20% per volume, without changing all of your end use, all your end use devices. So you need to change your boilers, cookers, and everything else if you go for 6%. So 6% is a practical minimum. After that, you'd probably jump to 100. We did ask whether you could convert existing gas networks to deliver hydrogen, and 3 models allowed you to do that, and the rest did not. Of course, in some cases, the countries had very limited or no natural gas networks, so it wasn't really an issue anyway, an option anyway. We asked about the various delivery technologies, including liquefaction, pipelines, road tankers, refueling stations, and storage. And you can see that the amount of hydrogen delivery and storage infrastructure varies quite widely between models, but it's much patchier than end users was. And there's some technologies such as gas field storage, on-site production of hydrogen or refueling stations, where there's only one model that is representing these. We asked how, for models that did represent these types of delivery technologies, we asked how they did that. And there's a couple of methods used. So some used a compound technology, so they defined a series of a supply chain, essentially, a series of supply chains, and each part of the supply chain, each supply chain they defined had a number of technologies in it to compress, store, and deliver the hydrogen, such as the one shown in the purple box here. Other models took the approach where each component of the supply chain was represented by a separate technology, and they could be mixed together as the model found appropriate. So shown by the green boxes here. And there was a mix between the two. So two models had only components, two models used only the compound approach, 3 used a mix of the two, and 3 models didn't provide any information about that. Finally, we asked about production technologies, which ones are in models, and this also varied quite a lot too. So it's probably not a surprise to everybody who's been on the call so far that most models had electrolyzers in them. And I think the 2 that didn't here have since had them added. But there's also quite a large number have gas SMR and have biomass. But once we started looking at the CCS technologies, bio-oil, waste, and such like, then very few models have these included in them. So they're much more variable beyond the basic set of technologies. So the conclusions that we came with, first of all, the level of modeling detail varies widely. Most models contain a basic set of technologies, but some of the more exotic ones were considered in very few models. Modeling the delivery technologies is particularly difficult. There's much, and we can tell that because there's much diversity between models. Now we have to keep in mind that production costs are normally much higher than delivery costs in most locations. You have to be a bit careful saying that because it depends on your delivery mode and the local geography. But that means for most models, if you capture the cost of production, you're capturing most of the cost of the hydrogen. So while we found that most models consider delivery systems, few offered a really wide range of different delivery systems. We were quite surprised how few models considered pipelines, actually. I think that's starting to change. Many models allowed hydrogen to be used across several sectors, but few considered in the transport sector and uses outside of road transport for rail, aviation, and shipping. And a number of demand-side technologies were not really considered in the model comparison, but we found very few models that considered any of these technologies. So some questions that were arising. First of all, would we benefit from disaggregating some technologies within the model in future, particularly electrolyzers, where we see different types of electrolyzers being used for different applications in the real world? Should we try to have a more comprehensive coverage of hydrogen production technologies across the models? Should we have a much broader focus on hydrogen-based compounds as well as hydrogen, such as ammonia and liquid organic hydrogen compounds? So these are not generally considered by energy system models, but there's an emerging view that trade in these types of compounds might be quite likely in the future, international trade. So that's something that we should be considering. There's questions about how we model hydrogen delivery systems. What are the costs of pure hydrogen compression and purification, and how should we represent these in the models? And finally, on injecting hydrogen into existing gas streams and on converting existing gas networks to use hydrogen. Now I want to talk a little bit about the outputs. And for the outputs, we ask each team to provide hydrogen output data for 2 scenarios from the model. The first scenario was a typical optimal scenario. So that maximizes model flexibility essentially, but it's the base scenario of the model minimizing cost to see how much hydrogen would come in the base run, the lowest cost run. And then the second scenario was a high hydrogen scenario. So in this scenario, we asked the modeling teams to put in additional constraints on the optimal scenario to maximize hydrogen consumption across the economy. And we asked them to make their own choices about what they thought was appropriate in the model to produce each of these scenarios. We had input from 7 of the models for these 2 scenarios. And so this is the list of the total hydrogen production in each of the scenarios. Now you'll see that a couple of the models have 3 scenarios, not 2. And that's always the case when you're trying to get academics to do something. There's always a subset who will never do what you ask for, or exactly what you ask for. But we were able to interpret those scenarios in one of the 2 previous categories. Now you can see that total hydrogen production varies quite a lot between scenarios. But that's kind of a bit meaningless because we have quite different sizes of energy systems between these models because they represent different geographical locations and different numbers of people. So a better way to look at this is in terms of hydrogen production per capita. And so that's what we do here. And you can see the second column is the gigajoules per capita in the optimal scenario, and the third column is the gigajoules per capita in the high hydrogen scenario. And it's often except for Japan, it's 2 to 3 times higher usage in the high hydrogen scenario compared to the optimal scenario. But there's quite a lot of variation between models. And particularly the UK Times and the Times Portugal model have much higher hydrogen production, hydrogen consumption per capita than the other models. And that was really interesting for us because I'm not going to go back to show you, but those 2 models had the highest number of end users available. And so it suggested that the number of end users suggested to us that by adding more end users, there was great uses of hydrogen, and hence in many of the other models, because they had a limited number of end users, they effectively weren't finding the optimal energy system, and that there likely would have been a higher use of hydrogen within the scenarios in the other models if they'd allowed more uses to actually happen. But they hadn't done that. So that suggested there was an area of further model development would be valuable here. This is a graph of how much hydrogen there is over time from 2020 to 2050 in each of the models. Remember, we started this before 2020. And this is all normalized to the amount of hydrogen that's used in energy in 2050. So this gives you an idea of how quickly the economies ramp up before 2050. And you can see it's quite varied, particularly in 2040, but still in 2030. And I'm going to, given time, I'm going to move on a bit. The next graph shows the fraction of hydrogen production from electrolyzers over time. Now, there's several models that use only electrolyzers, but not necessarily through the whole time horizon. And there's one model, the UK Times, didn't actually use any electrolyzers, I don't think, or very little. So this is all quite varied. There wasn't really a clear trend. If I do look at the fraction of hydrogen from each production route in 2050, interestingly, 4 of the models have almost all production from a single technology. The JMRT has most production from electrolyzers, with a little bit of leftover stuff from industry. And the remaining 2 models have quite a wide mix of technologies producing a broad portfolio of technologies producing hydrogen, 3 or 4 technologies. So quite different behavior between models there. And that's reflected in the fuel consumption, where 5 of them have virtually the same, virtually 100% production from a single fuel, while the other 2 have quite a mix of fuel inputs. On the consumption side, you can see there's a number of models that focus primarily on transport. But some do focus elsewhere. So JMRT, the Japanese model, focuses on residential and services, actually, so primarily for heat. UK Times has a mix between industry, electricity, and services primarily, with only 2% used in transport. So it's quite different. Those two models are quite unusual, that they have a very small transport component. And they assume that transport's primarily electrified. Other models, such as Irish Times, have 100% use in transport. In general, most of the uses across the models are between industry and transport, though. Within the transport sector, some models focus on heavy goods vehicles and buses, while some models have quite a mix between various areas. So the global model actually mainly uses it in aviation. The Japanese model mainly in cars, and then the rest are a little bit more mixed. So I want to finish off by talking about methods of representing hydrogen in energy system models. And first of all, we have to accept that not all hydrogen is equal. It can be delivered as a gas or a liquid. The gas pressure can range from a bar to 850 bar at end use, purity from 75% to effectively 100%. We can mix it with natural gas. There's a number of hydrogen-rich compounds. And so we have to, we talk about hydrogen, but there's lots of different types of hydrogen and grades of hydrogen that maybe we need to start thinking about within these models, because these models normally do just consider hydrogen as a single concept, as a single type of commodity. We need to think about what level of complexity in the representation of hydrogen is appropriate to a particular model. So in the boxes on the right, a full detailed hydrogen system might be very large, but a typical model is likely to be smaller than that. And the global model is likely to be even smaller because it's got so much of a broader scale. It's not feasible to do a very high detail and resolution on a very, very large geographic model normally. Within these models, we have a traditional approach of modeling a hydrogen system where we produce the stuff centrally. Maybe we convert it to ammonia, methane, or jet fuel. We then trade it, distribute it. Then we have a decentralized production and storage if necessary, and it goes to end users. But in reality, production looks quite complicated. So this is an output from an infrastructure planning model for the UK, showing how infrastructure might develop over several years, and trying to represent all of the various types of pipeline and pipeline length and cost and such like in a model without spatial resolution, such as UK Times, which is a single region model, is very difficult. And getting those costs looking sensible is very difficult. We have to keep that in mind. And even in practice, we have decentralized production and centralized production, which both contribute to end users and the hydrogen from each can be mixed with the other one. So it's much messier. And so we have put together what we think is an appropriate energy system for a large model. This is it. And I know you can't read this, but you are able to download the report. I'll have a link at the end if you're interested in seeing this picture in more detail. Essentially, it's quite complicated, and this is for a global model and all of the different bits that you might have, and it takes account of pressure and purity as part of the delivery system. It also accounts for synthetic fuels and ammonia and such like. So I want to briefly finish on my views on best practice modeling. So first of all, you need to carefully consider the breadth of the hydrogen system, including a wide range of potential end users across sectors, producing hydrogen from both fossil fuels and electricity, including hydrogen-derived fuels, including ammonia and synthetic jet fuel, and thinking about the international trade of gaseous and liquefied hydrogen and ammonia, which could be quite substantial in the future. We need to think about the model balance, making sure that we have the right appropriate size of a hydrogen sector within the model, but also making sure that the costs of hydrogen are consistent with the costs of other parts of the model, so we can make an appropriate comparison. So, for example, hydrogen production costs should use a consistent methodology with electricity generation costs, Otherwise, you're going to get more electricity or more hydrogen if they're out of sync. And we have seen that before in models. If you're going to include delivery infrastructure for hydrogen, then you need to also include delivery infrastructure for alternatives to hydrogen and vice versa in order to balance off the best uses of hydrogen and other solutions to meet future demands. The reference energy system design should reflect the likely use of hydrogen and the geography of the region. So, for example, and whether, for example, it would be centralized or decentralized. And we should try to represent the limitations of infrastructure in the early stages of hydrogen take-up. So we can't immediately go from no hydrogen to a huge amount of hydrogen across the economy. We don't have the capacity to build the pipelines, to build the electrolyzers and everything else. So we need to make sure that the limitations we have on making new infrastructure and how it goes upwards are taken into account in our models. With that, if you're interested in the report, there is an accompanying report to all of this work, and you can also download the data spreadsheets. I think they're anonymized, but you can download the spreadsheets and look at them, the final data that we used and that are represented here, and that's all available at this link. Yeah. So thank you very much for your time. I'd be very happy to take any questions.
Thank you, Paul, for your presentation. It was very useful. I don't know if we have any questions. If you have a question, just raise your hand or put it in the chat.
Yeah.
Okay, so Harry is saying that's very interesting to see the different approaches across models. Did you gather any information on different temporal and spatial resolutions the various models use for the hydrogen modeling?
Good question. So, not really, because these types of models are. I'm trying to think. I'm trying to remember. I'm not certain. I'd have to have a quick look and get back to you to be certain on the temporal side. Most energy system models have a fairly small number of regions and a very low resolution temporally, very low temporal resolution. So, for example, the UK model has one region and has 16 time slices to represent the whole year. So that's one typical day in each season split into 4 parts. So that's very very aggregated spatially and temporally. The global model I talked about has 16 regions. So those regions trade each other, but you're representing the world in only 16 regions. And that only has 6 time slices. So summer, winter, and intermediate with a single typical day with day and night done separately. So that's even lower resolution. Now, people have run times models to 200, 400 time slices, but it's fairly rare. Most of them are 20 or under. So I don't think we collected the data on that, but that's because we knew that however they're modeling it is never going to have the resolution of the electricity system to really understand the role of using hydrogen to balance the electricity system properly. Normally we'd run an external model alongside the energy system model and use that to parameterize any costs or opportunities of supporting the electricity system from hydrogen within the energy system model.
Great. So thank you for your answer, Paul. I saw that Rob had his hand raised. Do you have any questions, Rob?
I did have, but like I said, I wanted to move on. Paul, can you hear me okay? Yeah. I should have asked this question a very long time ago, but I thought it might be interesting for everybody else that's well known. The diagram that you had that had Japan with 100% cars for hydrogen consumption, that kind of surprised me as an outlier. Maybe you don't know because you didn't do the work, but any comments?
Okay, so that wasn't saying that Japan are going to use only hydrogen for their car fleet. That was saying that within the transport sector, where Japan uses hydrogen for transport, it only uses them in cars.
Yeah, exactly.
But in practice, a very small amount of, in practice, I think they used a very small amount of hydrogen in the transport sector. And my guess is that most cars wouldn't be using hydrogen, they'd be electrified in Japan in that model.
I understand that.
I don't have the statistics.
I'm surprised that there's no trucks, for example, that are using hydrogen in that model. But
yeah,
it's okay. Whatever.
that was the model output. I mean, it doesn't mean that it's the Japanese strategy.
Yeah, that's right.
You have to take, like any model, you have to take it with a bit of a pinch of salt and think carefully about what it's telling you and why.
Yeah.
We didn't go back to ask.
Excellent. Thank you.
Great, thank you. We have one more question from Francesco Gracheva in the chat. He asked, have you found that someone has addressed the issue of carbon neutrality of synthetic fuels, which implies modeling of green hydrogen plus CO2 from the atmosphere, not from power plants?
Okay, so these models should account for that if they've been set up properly. So when we set up energy system models, I showed you the supply chains we had earlier, and we can put an emissions counter at any point of the supply chain. So for example, if we dig up natural gas from the ground, we could, and there's some leakage from that, say 3%, 0.5%, whatever it happens to be, we can make that as a gas. We can count that gas leakage as methane going into the atmosphere as a greenhouse gas. And all the way down the system, whenever we create greenhouse gases, we can include those. Certainly within the UK model, we have CO2 capture and the use of CO2 capture plus hydrogen to make synthetic fuels. We didn't have that when that survey was done, but we do have it now. And we also consider synthetic fuels for jet fuel, and we also consider high value chemicals, producing methanol and producing ethylene, propylene, BTX, and other things from both biomass and from hydrogen plus CO2. So I think the broad answer is yes, and model neutrality is considered in that because, well, the CO2 can come from a number of places within the model, but the model counts total CO2 and needs to meet net zero. So either it will take it out of the air using direct air capture, or carbon captured from biomass or from industry. But even if it took it from coal, then it would need to offset elsewhere in the system in order to do that. So overall, the model will take account for carbon neutrality of synthetic fuels.
Okay, very interesting. I believe we have one more question. Yes, the per capita analysis done. Okay.
Yeah. Okay. So the per capita analysis was done on consumption rather than on production. So you're right. It would be different if for countries who are going to export hydrogen. Although in practice, Japan would be an importer. The global model, it doesn't matter anyway because we're including all consumption and production globally. And the rest of the models were European and would probably be primarily producing their own. I don't think they wouldn't be exporting. They might export a bit, and some countries have thought about it, Portugal and the UK in particular. But I think most single region models assume that they would. In fact, I think most country level models by 2050 assume that there isn't any hydrogen trade. So essentially, everything they produce, they need to consume as well. I don't think it's a very good assumption, and it's done because we don't have a good idea of what the boundary conditions should be about how much hydrogen would be available from trade or ammonia or LOHCs, or what the cost would be. And that's something that we're now working on at the global level to do better global models in order to produce boundary conditions for our national models. But at the minute, they assume there is no trade, and therefore production and consumption are actually the same. But it was consumption.
Okay, great. Thank you. Do we have any more questions? Or shall we go with the conclusions and overall recommendations? Okay, so Fabian is congratulating for the amazing work. So thank you, and we will forward you the slides of the workshop and the final report. Okay, so yes, Rob, I think it's your turn to present the conclusions.
Oh, good. I'm not record. Play slideshow. Start. Here we go. Yeah, many thanks, Omar, and thanks to Paul and your crew. It's pretty amazing collection of work. It's a lot like the opposite end of the spectrum of what we did in the entire task relative to what I presented, which was just focusing exclusively on electricity and hydrogen, well, electricity and electrolyzers. So just to conclude and hopefully invite some last minute questions, yeah, the crux for me of what's interesting about hydrogen is that there's nothing else that can do all these things of electricity consumer and network balancing, which go together hand in hand, and curtailment avoider, again, that's more of the same in some ways. Large scale carriers, so you put hydrogen in ships, and there's a fuel source. Coal is a fuel source, but hydrogen can do all these other things. And as a large scale green energy storage provider. Yeah, so all of these things involve time variation. The time scale of large scale storage is months. And as Paul pointed out, the time scale of some of the ETSAP models is 16 slices per year. That's fairly coarse. But for ancillary services, you get down to seconds. That's not just, its dispatch interval is 5 minutes, but ancillary services is even sub-seconds to respond quickly to network hassles. So how do we deal with that? And multiple resolutions is, multiple resolution analyses is, in my view, crucial to getting all of these benefits, all of these bullet points, as well as all the stuff that Paul has talked about. So, and then finally, just to highlight Paul's, one of the many things from Paul's talk, that ETSAP reference energy system designs need to account for the anticipated hydrogen consumption technologies and derivatives and so on that didn't do very well before this task or before 2018. So, questions, please. Oh, how do I unshare? There we go. There we go. Questions for either Herib or Daria is probably not here anymore, but Paul is hopefully not gone away. Uh-oh.
Yes, I think Paul's not here.
Okay, he took off already. Yeah, everybody's pretty busy. I guess Daria rocked up and then took off. Oh, Paul, there you are. Cool. Herib, are you there still? He might have gone, or anyways.
Yes, so do we have any more questions on some of the sections or on the overall results achieved by the task? We have like 5 more minutes for any particular or general questions if you want to ask.
And bear in mind that you will get an email link to the recording, as well as an email link to the final report in glossy graphics designed format quite soon. Hopefully at the same time.
The recording will take at least 1 day to be available on our YouTube channel, but the final report will be today for sure.
Yeah. On any recommendations for follow-up studies, if you Marcel, hey Marcel, how you doing? If you scroll up to Jonathan's recommendation in the chat about 1 page up, at 6:48, he recommends a follow-up task that focuses on policymakers to how to make best use of this stuff. Yeah, and he got Jonathan got 6 thumbs up. Yeah, the transition from theory to, hey, let's get all these models together, to hey, now what do we do with it, needs to be, yeah, it would be quite productive build a bridge between what we've done and policy makers. So yeah. How about Paul?
Thank you.
Is Paul Lucas still here? I don't know if he has any questions. He's probably gone.
Let me check, but I don't think so.
Whatever.
No, I think he had to jump to another meeting.
Yeah, no worries. All right. Very good. If there's no other questions, should we wrap up? It's coming up to 8 o'clock here in South Australia. So I'm not ready for bed yet, but I certainly maybe dinner time anyway. Cool. All right. Yeah, and thanks again, Omar and crew at IEA. Done a great job.
Thank you. Thank you for your presentation, for the hard work during these past years, and we hope we can continue with another task or collaborating. And thank you all the attendees for attending the workshop. We will forward you all the information, and we hope you enjoy it, and just stay tuned for more workshops, publications, final reports. We will be launching soon some more reports, so just stay tuned on our social media. And thank you very much.
All right. See you all next time.
Bye. Thank you.
Thanks, everybody. Bye-bye.